In this section, we're going to talk about redox reactions and batteries. First, a little review on redox reactions. The term redox is short for reduction oxidation. We learned earlier that each redox reaction can be thought of as a combination of two half reactions. Those half reactions are balanced for both matter and charge. The reduction half reaction takes in electrons, while the oxidation half reaction gives up or furnishes those same electrons. They depend on each other since the electrons generated by oxidation are simultaneously used in reduction. So the number of electrons lost is equal to the number of electrons gained. In batteries, the half reactions are separated so that an electromotive force or EMF is generated, which drives the flow of electrons from one half reaction to the other when the circuit is closed. Remember that EMF is measured in volts, and that the EMF of a battery can drive electrons through an electric circuit. To see how that voltage is generated, we have to review our understanding of redox reactions and then apply that understanding to batteries. In any redox reaction, electrons are transferred between reactant and product species. As a result, the oxidation state of at least two species are changed. In order to keep track of which species loses electrons and which gains them, we assign oxidation numbers to individual atoms in the reaction. Here's a review of oxidation numbers. Remember that elements in their elemental form have an oxidation number of 0. For a compound, the sum of the oxidation numbers in a neutral compound must be 0. For an ion that's a single atom, a monatomic ion, the oxidation number of that ion is the same as that charge. And for a polyatomic ion, the sum of the oxidation numbers is the charge on the ion. The oxidation number for hydrogen is -1 when it's bonded to a metal and +1 when it's bonded to a nonmetal. Fluorine always has an oxidation of -1, as do the other halogens usually, but they might have a positive oxidation number in an oxyanion, as the example here shows. In this ClO3- anion, chlorine has an oxidation number of +5 because the oxygen is -2, and so we have -6, and we have to have overall of -1, so the chlorine is +5. Nonmetals usually have negative oxidation numbers, although some are positive in certain compounds or ions. And oxygen has an oxidation number of -2, except in the peroxide ion when it is -1. Take a look at this reaction between zinc metal and acid. Determine the oxidation numbers. Then move the box to check your work. So I'm going to talk you through this. Remember what we said about the oxidation numbers for metals in their standard elemental form and that of monatomic ions, because that's what we have here. We have 2 elements and 2 ions. So take a minute and then I'll move the box. Is this what you got? Zinc solid metal has an oxidation number of 0 because it's in its elemental form. The hydrogen ion has an oxidation number of +1. It's a monatomic ion with a charge of +1. That's also why the zinc ion is 2+. And hydrogen gas is in its elemental state, so it has an oxidation number of 0.